Time for section 1.4, measuring angles. Angles will be used a ton all course long, so let's delve into some of the basics about them. And nothing is more basic than its definition. An angle is formed by two rays that have a common endpoint. You probably already have a sense of what that is and or what that looks like. Here's a lovely angle. Let's deal with some angle anatomy. First, the rays are known as the sides of the angle. And the sides of an angle are always rays. So if a problem asks you, what are the sides of an angle, your answer had better be two rays. Then we have the common endpoint, which is known as the vertex. One last anatomy detail. We have an interior and exterior of an angle. First, the interior. Interior should sound like at the inside, and that's exactly what the interior of the angle is. You can think of the angle as some beast. I'm sure my lovely drawing skills are... And everything that beast is about to chomp down on is on the inside. Given all that, it should be obvious, but point A is definitely on the interior of the angle. It is definitely going to be lunch for our geometry beast. But let's do one a little harder. Does point B count as being on the interior of our angle? The answer is yes. Remember that these angle sides are always rays and are always going on forever. So even though our sides haven't been drawn long enough for point B to look like it is on the interior, the angle does go on forever, and point B is on the interior. Now for the hardest one. Does point C, which is on the side of the angle, count as being on the interior? What does your gut tell you? Do you think the edge counts? The answer is no. Point C is not on the interior. The edge does not count. So now the exterior of the angle. You can probably guess at this point, but if this part is on the interior, even the stuff way over here, then this part must be on the exterior. Pretty simple. Given any point on the plane of this angle, it will always be one of three things. Either on the interior, on the exterior, or on the edge, on top of the angle, which is neither on the interior or the exterior. Now that the anatomy is out of the way, we now have to deal with the naming of these angles. There are three ways to name an angle, so let's take care of them one at a time. Points are named with a capital letter. Lines are named with a lowercase letter. Planes can be named with a capital letter again. So what about angles? What do we label angles with? A number. So with this angle now labeled with a 1, we can now call this angle 1. However, angles are going to come up a lot, and we certainly would hate to have to write it out all the time. So usually you will see the angle symbol instead of it written out. The angle symbol looks like this. You'll be seeing that a lot. So this is the first way you will name an angle. The second method requires us to label the vertex as well as one point on each edge, like this. With these points labeled, we can now name this angle. When you name an angle using this method, you use all 3 points, but the order you use the points absolutely matters. You must start at one of the points that is on the angle side, then go to the vertex, and finally use the point that is on the other angle side. The end result of this is that you should end up tracing your angle like this. Start at one side, go to the vertex, go to the other side. It ends up tracing the angle. Since I started at A, went to B, and finished at C, I can name this angle ABC. Would it matter which side I started with? Could I have started with point C? The answer is yes. You certainly could have. The only thing that matters is that you trace out the angle we have. So by starting at C, we could name this angle CBA. You still trace out the same angle. This is the second way to name an angle. And now to the third and final way to name an angle. The first 2 ways to name an angle always work. This third way to name an angle doesn't. So make sure you understand when you can and when you can't use this method. First, the basics. In order to use this method, you need to have the vertex labeled, just like in the previous method, but that's all. You simply use the vertex name as the name of the angle. So in this case, it is perfectly allowable to say angle D. This is perfectly allowable here, but what about this? Now you are not allowed to use this method to name the angle. What's the problem? Do you see? There are now multiple angles possible for angle E, and that doesn't work. On the left, when there is only one angle possible, go ahead and name it. Angle D is fine. But in the right picture, there is more than one angle there. So you are not allowed to name that angle angle E. Do you know how many possible angle E's there are? There's one here. There's one here. And then there's the really big angle. There are 3 angles there. Because there's more than one angle possible, you cannot say simply angle E. Angles are measured in degrees. So the first thing to know, or be reminded of, is that a full circle is 360 degrees all the way around. However, we will rarely see degrees written out. So the symbol for degrees is this. Hopefully that is already familiar to you. We will also be measuring our angles in degrees. When we measure it in degrees, we are basically asking how much of the circle it covers. This angle here happens to be 40 degrees. So that lets us know that this angle's size is such that it takes up 40 degrees out of the 360 degrees total in a circle. The common tool for measuring angles is a protractor. Let me plop a public domain one onto the screen that comes from the Wikimedia Commons repository. There are 3 things to notice about the protractor. First, at the middle bottom of every protractor, there is a little circle or a little plus or crosshairs for you to put right directly on top of the vertex. Then the numbers for the degrees run in 2 directions. Then the numbers for the degrees run both clockwise with a 0 at the far left and counterclockwise with a 0 at the far right. So if I wanted to measure this angle on the screen, I would take my protractor and line up the vertex with the crosshair and the side of the angle with the edge of the protractor like this. With the protractor now in place, we can start from the 0 and read going clockwise until we get to our angle and see that it is 113 degrees. If, instead, the angle is oriented this way, then we would want to use our counterclockwise number on the protractor. Make sure everything is lined up properly, and now we go counterclockwise, starting from this 0 and going this way until we find that the angle is 54 degrees. Lastly, there is one last way to measure angles, and it is covered by the protractor postulate in this section. The name protractor postulate isn't very helpful, and as you will see in its use, very few people would actually use a protractor this way. But in theory, this protractor postulate says you can use a protractor like this. In practice, nobody would actually do this. It is far easier to line up the edge of the protractor with the side of the angle. But protractor postulate says if you wanted to do it like this, then you have options. We can use the clockwise numbers, which in this case come out to 47 over here and 109 over here. Or we can use the counterclockwise numbers going this way, which says it should be 71 and 133. Then you can subtract one from the other. Take the absolute value so that you always end up with a positive number, and the resulting answer is always the same and always the size of the angle. The protractor postulate says just choose whichever way you like, you'll always get the right answer. The protractor postulate is not that important to remember, and it's not very practical, but it is the third way to use a protractor. Now let's say we've determined that the measurement of angle ABC is 44 degrees. That's too much writing. So we have an abbreviation for it. The little m stands for measurement. This works similarly to length, and it comes with the same pitfalls. Just like you can't say that a physical thing, like a line segment, can be equal to a concept like distance, and you have to use length instead to set something equal to a distance. Similarly, you are not allowed to set a physical thing like an angle to a concept like measurement. So you have to use measurement of an angle to set it equal to its degree measurement. Mixing and matching is not allowed. It's a tiny detail and one beginning geometry students often have trouble with or easily overlook, so just be careful. Physical shapes can't be equal to distances or measurements. Lengths and measurements can. Now we get to some classification of angles, some of which you probably have seen before. First up, the acute angles. Acute angles are defined as an angle whose measurement is greater than 0 degrees, but less than 90 degrees, just like the one on the screen now. Then we have right angles, which are exactly 90 degrees. Often if an angle is a right angle, it will be marked with a right angle symbol instead of 90 degrees. Most of you have probably seen that, but the right angle symbol looks like this. A little square box. Next up is the obtuse angle. Most people know that an obtuse angle is greater than 90 degrees, but there is also the second part of the definition that sometimes people forget, and that it is also less than 180 degrees. Most students will have already been familiar with acute right and obtuse angles. However, few of you will have seen straight angles before. They end up looking like a line. However, all the pieces for an angle are there. The vertex is point Y. Ray YX is one side of the angle. Ray YZ is the other side of the angle. Together, they all form straight angle XYZ. It's a new angle type to get used to. If you are ever asked to find a straight angle in a picture, you will need to be on the lookout for 3 collinear points. It's the only proper way to name a straight angle. Now let's look at congruent angles. Congruent is always and forever going to be things that are the same size and same shape. You must pass both parts in order to be congruent. So if we are looking to see if two angles are congruent, we already know they're the same shape. They are both angles. The only thing we need to check then is if the angles have the same measurement. If they do, then they are congruent. Here we have two angles with measurements of 44 degrees. So that's enough for us to declare that angle ABC is congruent to angle DEF. Hopefully that's pretty simple and straightforward. There will be times when we have two angles that we want to mark as congruent, but we don't want to, or maybe we don't even know, what the measurement of the angles actually is. Let's say these two angles on the screen are congruent. To mark angles congruent, we use these symbols. A single band or arc is used on each angle. Since each angle has one arc, they match up, and we have marked them as congruent. I don't know, and possibly don't even care, what the actual measurements of the angles are. All we care about is that they are congruent, which is what this shows. It is important that the two arcs you make are at different depths. Let's see why. These are the same angles. But if I use arcs of the same depth, it looks like this. It now looks like one big arc instead of two separate ones. In addition, this actually has a different meaning. You will see marks like this from time to time. When you have an arc that stretches across like this, that is how you demonstrate you are talking about the big angle instead of either of the smaller angles. So this is a marking you also need to get used to, but it does not show two angles congruent. For that, you definitely need arcs at two different depths, just like the left picture. There will be times when you want to mark multiple pairs of congruent angles, like in the picture here. We start by making the first set of angles congruent, like this. Then what about the second pair of angles? What should we use for them? For a second pair of congruent angles, you use a double arc mark, or double band, like this. There could be some situations where you might need three sets of angles marked congruent. So you use a triple arc mark, or triple band, and so on. Now this is the style of marking incongruent angles that I use, and it is the style the book uses. From here on out, that's all you will be seeing in this course. However, there is another way of marking angles congruent that is fairly common too, albeit not as common as this method I have already shown you. The other style looks like this. I am showing you the style to expose you to it so that if you ever see it later, you know what it means. It's just a different way to do the same thing. Always use single arc marks, and then the tick marks are used to show how they match up. I won't care if you prefer to use that style yourself, but you won't see it from me again. Say goodbye. There have been a few postulates this chapter, but there are only two that you really need to know the names for, as they will come up in proofs quite a bit. The segment addition postulate, which we did earlier, and now this one, the angle addition postulate. Like all postulates, it's fairly common sense, but here's what it says. The wording of the postulate is in math speak, which is like a foreign language to many of you, but you will need to get used to it a bit. The wording of the postulate obscures the fact that this is a really simple concept. The name angle addition postulate tells you what we are doing, adding two angles together. So basically we're saying that if we take this angle and add it to this angle, then we get the really big angle. That should be so simple, stupid, obvious, take your pick, that you get the familiar, well duh response. This postulate is one of the important ones to know. Some teachers will make you spit it out and memorize it, but all we will be asking you to do is to be able to identify when it is happening. When two angles are added together to make a bigger angle, or if you break down a big angle into two smaller pieces, then you just need to identify that the angle addition postulate is the reason why you were able to do such a thing.